Hey, welcome to The Explainer. Today, we're going to dive into something really, really cool. It's this new method called CTEntropy, and it might just be the key to cracking the brain's code. So, let me ask you something. What if our brains are speaking this incredibly complex language? And all this time, we've basically just been hearing the mumbles. For decades, we've had tools like the EEG to listen in on the brain's electrical activity. And look, they've given us some amazing insights. But what if I told you there's a whole other layer of information in that chatter? A layer that we've been, well, completely missing. All right, so let's get into it. First up, we need to talk about this hidden language of the brain and why the ways we've been listening so far just might not be enough. So here's a good way to think about it. Usually when we analyze an EEG, we're looking at the big stuff, the power, the frequency, the rhythm of the brainwaves. It's kind of like listening to this huge, beautiful orchestra, but only paying attention to the loudest instruments, like the booming drums or the blaring trumpets. Sure, you get the beat, you get the volume, but you're missing pretty much everything else. And that's the big question, right? What about the complexity of the whole symphony? What about the quiet interplay between the strings and the woodwinds? The unexpected notes, the little bits of improvisation. That's where the magic is. That's where the real story is. And that brings us to a totally different way of listening. So let's talk about how we can actually measure that complexity. Okay, the key idea here is something called symbolic entropy. And I know that sounds super technical, but stick with me, it's actually pretty straightforward. All it really is a way to measure how complex and unpredictable a signal is. It basically quantifies how much information is hiding in those patterns, not just how loud they are. So think back to our music analogy. A signal with low complexity that's low entropy. It's like a nursery rhyme, twinkle, twinkle, little star. It's simple, it's repetitive, you always know what's coming next. But high complexity, high entropy, that is a wild improvisational jazz solo. It's totally unpredictable, and every single note is packed with new information. And that's the goal of CTEntropy, to finally hear the brain's jazz solo. Okay, so how do we actually do that? How do we listen for the jazz? Well, that brings us to the method itself. CTEntropy. It's actually a pretty clever three-step process. First, it takes those raw, messy brainwaves and converts them into a kind of symbolic language. It's almost like translating a recording into sheet music. Then, it analyzes the complexity of that new language. And this is cool. It does it at multiple timescales, looking at tiny fractions of a second all the way up to several seconds. And finally, from all that, it creates this unique entropy signature. It's like a personalized complexity fingerprint for a specific person's brain activity. And when you put it side by side with the old ways, you can really see what a big deal this is. Instead of just looking at frequencies, we're now measuring actual complexity, the information itself. We're going from these rigid, fixed frequency bands to a system that adapts to the brain's own language. And maybe the biggest game changer is this. We're moving away from just looking at population averages to creating these unique individual signatures. And we can do it all within one single unified system. Okay, so the theory is awesome. The idea is great. But does it actually work in the real world? That's what we're going to look at now. How they put this thing to the test. Yeah, this wasn't just some idea on a whiteboard. The researchers went and grabbed a bunch of big public datasets. Real data from studies on things like alcoholism and epilepsy. They wanted to see if these new entropy signatures could actually, tell the difference between a healthy brain and one with a specific condition. And get this, the results were pretty incredible. Just by looking at the data from a well-known alcoholism study, this method was able to tell the difference between subjects with alcoholism and the control group with 86.7% accuracy. And that's based only on the complexity of their brain's signals, nothing else. And when you actually look at the numbers, you can see it plain as day. The average complexity, that entropy number we talked about, it's measurably lower for people with alcoholism and epilepsy compared to the healthy control group. It's almost like we're finding a quantifiable neurological fingerprint for these conditions, hiding in the signal's complexity. And check this out. When it came to spotting epileptic seizures, the signal was just massive.
The paper talks about a large effect size. Now, what that really means in plain English is that the drop in brain complexity during a seizure isn't some tiny little fluke you have to squint to see. No, it's a huge, unmissable flashing red light that this method picks up loud and clear. So, what's the big picture here? What could this all mean for the future of brain health? That's what we'll cover in our last section, the possibility of a new era for diagnosis. The potential here is, honestly, huge. Think about it. Instead of needing a whole bunch of different super specialized tests for every little thing you want to check, you could have this one unified system. It could totally open the door to doing broad neurological screenings with just one EEG. And the possible uses just go on and on. For epilepsy, maybe you could find patterns that predict a seizure before it even happens. For addiction, it could help us spot those subtle changes in the brain. And for diseases like Alzheimer's, it could give us a brand new way to track how the disease is progressing. Okay, but here's a really important disclaimer. Right now, CTEntropy is a research tool. A very powerful one, but still a research tool. Before a doctor could ever use this to diagnose you in a hospital, it has to go through tons of clinical trials and get the green light from places like the FDA. We're not there yet. So I want to leave you with this thought. What if, by finally learning to hear the whole symphony of the brain, not just the drums, what if a single, easy brain scan could one day screen for dozens of neurological issues, maybe even catching them at the very earliest stage? It's still early days for sure, but that's a pretty incredible future to think about.